Hello, everyone, and thank you for joining us today. I am your host, Shannon, and welcome to the webinar. Sorry, can you hear me okay?
Yes, we can hear you.
Oh, great. Sorry. Sorry about that. Thank you again. Welcome to the webinar, What You Need to Know About Measuring Torque. Before we begin today's presentation, I would like to review a few housekeeping items with you. Please take a moment to observe the tools available in the WebEx event window. Now, everyone's microphones are muted during the webinar. Please do not forget to activate your PC speakers to enable audio or connect headphones to your PC. You may have to take the step of joining the audio conference to hear sound. Please type any of the questions you have into the WebEx Q&A dialog. You can open the Q&A window by selecting the Q&A icon in the WebEx toolbar at the top of the screen. All questions will be answered at the end of the webinar. Today's presentation will be emailed to all attendees. If you have additional technical questions, feel free to contact our technical support team at support@usa.hbm.com. Now, today's presentation will be brought to you by Krista Tweed. She is one of our application engineers, Genesis High Speed. She has a PhD in physics from the University of Wisconsin-Madison with 23 years of experience in high-speed electrical data acquisition. I will now like to welcome Krista Tweed to begin today's presentation.
Thanks, Shannon. Welcome, everyone. As Shannon mentioned, our topic for today is measuring torque ripple accurately, so we will jump right in. First, I'm going to do a quick introduction to HBK and just explain why we fit into this torque ripple measurement area. We'll talk about what is torque ripple, why we care about torque ripple, and of course, how you measure it. So HBK offers two product lines that play into measuring torque ripple. One is our edrive power analyzer, which can provide highly accurate, high bandwidth power measurements, as well as record the torque and speed signals all in one system to give you a time-aligned mechanical and electrical measurements at the same time. HBM is probably most well known for our world-class torque transducers. That's often how customers come to find out about us. Those torque transducers are incredibly accurate, up to 0.02%. And something not everyone realizes is they also have a high bandwidth for that measurement. So a 6 kilohertz bandwidth is very high for that torque measurement. And when you combine those two things together, the high accuracy and the high bandwidth, it means that you're able to really measure small changes in torque at higher frequencies and really believe those measurements and know that what you're seeing is real and not just noise. So when we combine that high accuracy torque transducer with the edrive power analyzer, you really have a unique tool to allow you to view the dynamic behavior of torque. And that's what we're going to look at today. So what is torque ripple? Torque ripple is really the dynamic part of torque that rides on top of that steady state condition. So I've got an example graph here in the upper right that shows a load step being applied to the motor. And I'm showing you two different torque signals. The first is instantaneous torque or high bandwidth torque, and you can see that when that load step is applied to the motor, the torque really oscillates around in response to that load step before it settles off into a steady state. Now the black trace that you see here is a filtered version of that instantaneous torque signal. So if you're looking at filtered torque, which is what many data acquisition systems and power analyzers provide to users, you're not going to have any visibility to that dynamic behavior. And that's just not reality. What's really happening in reality is that the torque is oscillating around and changing very rapidly. And that can be important depending on what information you need out of your measurement, that you have accessibility to that. Now, even when we get out into the steady state here and things on the large scale look pretty calm, if we go down in the bottom graph where I've zoomed in around that steady state condition, we can see still the black line in the middle. So we've got a pretty stable average torque value. But in the red, you can see that instantaneous torque. And even at that steady state condition, the dynamic torque clearly has a periodicity to it. So that's the torque ripple that we're talking about. It's an AC component that rides on top of that DC average torque value. So where does torque ripple come from? Let's step back for a minute and think about how an electric machine works. Most electric machines are being powered by some type of AC electricity. In traction applications, it's usually three-phase excitation, but in other applications, it can be more phases, maybe 6-phase or 9-phase. The example that I show up here on the right is a three-phase current, so you can see the blue, the black, and the red phases of the current. And the torque is going to follow whatever the maximum of the torque is at any given time. So you can see that in this bottom graph, we've just put a green trace following the maximum of the instantaneous current, and that's what the torque is, and that's where the torque ripple comes from. So you can clearly see the AC nature. The average torque value is going to fall right in the middle, but it's really got that transient oscillatory behavior. The frequency of the torque ripple is also going to be proportional to the RPM, to the speed of the motor. So the faster the fundamental frequency of the current, the faster the oscillations of the torque ripple. And the more phases there are in the system, the more ripples there will be per mechanical rotation. So a 6-phase machine will have twice as many ripples in one rotation as a 3-phase machine. The number of phases will also have an effect on the amplitude of the torque ripple. The more phases you have, the less amplitude you have there in the oscillation. Now the ripple can also come from the construction of the machine. So a permanent magnet motor is a good example of that, and that's what I've got shown at the top here. This type of motor is most popular for mobile applications or power-dense applications. In a permanent magnet motor, just like the name says, there's a magnet that's always on, spinning around the rotor. If you ever have a chance to walk up to a permanent magnet machine and try to spin the shaft when it's not running, you're still going to feel these bumps that you have to overcome as you spin it. And those bumps are when you're pushing the magnet through the stator slots. The stator is a big chunk of iron, and the magnets naturally want to attract to that iron. And so you kind of have to push them through those slots to overcome that magnetic force. Once the machine is spinning and under excitation, you're still going to get that magnet-stator interaction, and that's what causes the torque ripple in those types of machines. Now with a reluctance-based machine, there's an example in the lower left here, you have a chunk of iron in the middle with pulses of current going through the stator windings. The iron in the middle is going to interact with the magnetic field set up by those pulses, and you get a similar behavior. So you get hard torque pulses as it spins, as that magnet jumps between the various points where it feels the highest magnetic force. There's going to be a lot of noise and vibration issues with the reluctance machine because of those hard torque pulses. And a final example in an induction motor, which has been the workhorse of industry for more than a century. If you walk up to an induction motor and try to spin the shaft, it's going to spin freely when the motor's not under excitation. However, as soon as you apply 3-phase power to the stator, you induce magnets in the rotor, and the iron bars in the rotor become little magnets. You can see that a little bit better in a blown up picture here. So as this spins, you're going to have that magnetic force as it jumps from slot to slot. You're going to get little tugs and interaction, and that's where the torque ripple comes from. So how torque ripple looks for a specific motor is strongly determined by the construction of the machine. How many slots there are, how many windings there are, what the magnet on the rotor looks like. So let's look at an example for a permanent magnet motor. This example you can see is a 3-phase excitation. Here's my 3 phases of current in red. The blue signal is the torque. And you can see that oscillation, that's the torque ripple. If we look, we've got about a 20 Newton meter average torque value, if we just kind of look at the average of that blue trace. And we can see if we look at one full cycle of the electrical signal, we've got 36 ripples per electrical cycle. Those 36 ripples are coming out of a variety of variables for this particular machine. The three-phase excitation, the number of slots in the stator, the number of magnets in the rotor, and whether there were any suppression techniques in use or not. All of those are going to affect how many of those ripples we see per electrical cycle. In this example, we've got about plus or minus 1 Newton meter of ripples sitting on top of that 20 Newton meter average. That's pretty significant, 5% of the average value. So that may be something in this case that the operators want to try to mitigate and decrease. Now, if we increase the frequency of the AC excitation, then the current frequency increases, and that's also going to increase the frequency of the torque ripple. So the motor construction determines the number of ripples per electrical cycle, and that frequency of the ripple is also proportional to the rotational speed. The amplitude of the ripple is harder to predict. That's really going to vary with operating conditions, and there's not kind of a hard and fast rule that lets you predict what that amplitude is going to be. So why do we care about torque ripple? Noise and vibration is a really big part about why we care about it. The most important concern is probably the amplitude of the torque ripple as a percentage of the average torque value. A rule of thumb I've heard from customers is to keep torque ripple to less than 2% of the average, but the requirements will really be dictated by the application. Large torque ripple can result in difficult vibrations that can adversely affect the user experience for the product. Ripple frequency and amplitude can be affected by the motor control technique as well. We'll look a little bit more at this later, but how the motor switches its control mechanism and how it's programmed to run can increase or decrease the amplitude of that torque ripple. And being able to measure the torque ripple and understand how it's reacting to various control techniques can be very important for the operators to make decisions on how they want that motor to run. And a final note, we're really seeing that speeds are increasing greatly. So operating at 20K RPM for an automotive application or even higher in the aerospace applications is not unusual. All of that is going to increase the ripple frequencies and the vibration and increase the challenges in making that measurement. Now, what about when the test stand has a gearbox? The data shown here is taken from our little dyno demo test rig that we have. It has a permanent magnet machine going into a gearbox. So my colleague Mitch recorded this data. You can see he did about a minute of data of moving that machine through torque and speed ramps to try and find a place where the ripple was the highest. So in the top graph, you're seeing the overall full test. You've got maybe 45 seconds of data there. The red trace is the high bandwidth torque, the instantaneous torque, and the blue, which you can just see in the middle of the red, is the average torque signal. Now, if we zoom in on that particular point where the noise looks higher, you can see very clearly that while that average torque value is pretty consistent, we really have clear oscillations, frequency and amplitude going on around that average value. That's real torque ripple. That's not just noise in the signal. And that can really be a problem in the situation with a gearbox because a gearbox can multiply or divide torque, so increase or decrease it. And knowing the peak values of torque being experienced by system components can have a big effect on the lifetime of those components and how well they hold up in the application. If all we can view is the filtered value, that average value, rather than the actual torque ripple, we're just not going to have visibility to those high torque swings that are happening in the system, which can affect how well our system operates the way we expect. So why is it so important to have an accurate torque measurement? And one reason with electric motors is efficiency. With an internal combustion engine, engine efficiencies were only, say, 30 to 40%. So if we were measuring efficiency with a 3% error, maybe we measure 39% instead of 36%, not really a problem. We still believe this, it's a reasonable result. But in the case of electric motors, motor efficiency can be in the range of 85 to 98%. Now, if we have a 3% error on a 98% efficiency, our system could tell us 101% efficiency. Obviously, that's not possible, right? We can't violate the rules of physics, and so our boss isn't going to accept that result. So having an accurate efficiency measurement in the world of electric motors is much more critical. Also, to highlight the importance of being able to measure very small differences in torque, there's a little math calculation here showing that if we have even a 0.25 Newton meter offset on our 38 Newton meter torque measurement, that gives us a 0.5% error on our power measurement. And that's going to go, that error carries right over into the efficiency measurement. So being able to measure torque very accurately has a big effect on the accuracy of our power measurement. And being able to have both an average torque value and that instantaneous is a great feature of the HBK edrive power analyzer. The reason for that is you really want that average torque measurement for your efficiency calculation, because you want to measure efficiency, the input efficiency, the power coming from your inverter, and the output efficiency, the mechanical power, over the same time signal, typically an entire rotation of your electric motor. So having a very accurate averaged torque value to get that efficiency improves that efficiency measurement. User experience is another reason we really care about torque ripple. So sometimes you can feel torque ripple in products, and one example is a vehicle, when the electric machine is clutching in a hybrid transmission, for example. If I've got friends who own electric cars, and I've heard them talk about the clutch closing on that electric machine, and they can really feel the car lurch when that happens. So it really feeds into that user experience, and that's dynamic torque behavior. I've seen a presentation where they talked about one of the big improvements in the Toyota Prius between 2004 and 2014 was a greatly enhanced suspension profile. And that came out of the design engineers doing a much better job of reducing the torque ripple so that the user didn't experience it as much. On the other side, sometimes you want to feel torque ripple. And a great example of that is an electric drill. I've seen a presentation by an electric drill manufacturer where they were talking about they had the electric motor in the drill designed so that when it hit its torque maximum, the speed just went to 0. Very elegant solution. However, they sent those drills out into the field to be tested, and the carpenters all came back and said, this drill is broken, it doesn't work right. And the reason was that they were used to feeling that drill clutch, and they weren't happy when that physical feedback went away and was no longer present. So the design engineers went back and they redesigned the product to add back in that clutch experience because it was really expected by the user. A final example is vibration. So this aircraft shown here is the NASA X-57 Maxwell. It's an experimental electric aircraft, and you can see it has 7 props on each wing. So let's imagine that the torque ripple in this outer prop induced a vibration in the wing that then matched up with a resonance of all of the smaller props here. Well, clearly that's going to be a concern with an electric aircraft because you don't want your wing to suddenly begin vibrating and react strongly to that vibration. So that's just an example of how user experience can play out. So measuring torque ripple, what do you need to do that? First, you're going to need a torque sensor with a high accuracy and a high enough bandwidth for you to observe the torque ripple. Second, you're going to need a noise-immune communication between the torque sensor and your measurement system. A lot of these systems are PWM driven, and analog signals are going to be very susceptible to noise in that environment. HBM torque transducers use a frequency output for both torque and speed. The torque output is a square wave. So for example, 60 kilohertz at zero torque, 30 kilohertz at maximum negative torque, 90 kilohertz at maximum positive torque. And the measurement system can read that digital signal and have a much more accurate and cleaner measurement than if it's trying to measure an analog value. Third, the acquisition system needs to record at a high enough data rate to be able to measure the full 6 kilohertz bandwidth of the torque sensor. We often run into customers who have spent the money to purchase a high-end torque transducer with a high bandwidth, and then they measure it with a system that measures at 10 hertz. And so they're not going to see any of the information occurring at that higher bandwidth. Now, for some applications, that's not a problem. But if you really want to be able to see the full breadth of information the transducer can give you, you've got to have a measurement system that can support that. And finally, having a measurement system that allows you to correlate all the signals of interest, the electrical signals, the torque and speed, maybe some vibration inputs, that can give the operator the clearest view of what's happening in the machine. So let's look at a few more of these in detail with some examples. On the bandwidth side, what I'm showing here at the top pane is three-phase currents. And what we've done is apply a load step to this machine. So you see the currents kick in. And very soon after the currents kick in, now we see the torque start to respond. I've got three different torque signals shown here. So it's the same torque measurement, but with different filters applied. The bright blue signal is the full bandwidth or instantaneous torque. And you can see that we get a really large swing with that instantaneous torque. It goes up to about a 50% overshoot there before it settles down into the steady state. The pink signal is showing a 100 hertz filter applied to that instantaneous or full bandwidth torque. What you can see there, of course, every filter results in a phase delay. So you've got shifted time information. You're not going to know exactly when the high maximum torque actually occurred in the system, but you also have a reduced amplitude because of the filter. So we're not having full visibility to the maximum torque that was experienced by the system. And as I mentioned earlier, knowing that maximum torque value can be really important to choosing the components of your system, making sure they're going to be able to withstand those high torque pulses, even if they're experienced very briefly, and also for understanding and predicting the lifetime of the components in the system. What kind of information is that component going to feel and be able to experience, and how long will it last with that high torque value applied? The third signal you see here is the green, and that has a 10 hertz filter on it. And with that signal, we're really not seeing any of the dynamic behavior at all. Now, in some applications, that may be fine. You may not need to know that. But if you're trying to, as I said, size components, predict lifetimes, really understand how your system is operating, that highly filtered signal just isn't going to give you the information that you need. The filters can be present not only in the instrumentation, but also on the sensor side. So one thing to be aware of, even if you have an HBK torque transducer, we offer internal filters. Not everybody wants to have that full bandwidth of information. So as you use those sensors, be aware of what filters are present in the system and make sure you've got them set the way that you want. Control change is another great opportunity to look at torque transients. So what we're seeing here in this data is a system as it's changed from PWM excitation to a 6-step excitation. So on the left side, we've got our PWM. You see a nice sinusoidal current there in the middle pane. You see the PWM voltage at the top, and you can see some torque ripple on the bottom, but it's not huge in magnitude and it doesn't look too excessive. Now we apply that change, control change, to a 6-step excitation, and suddenly we go from 13.5 kilohertz down to 500 hertz on the voltage. You see the current react, and it becomes, instead of being a nice clean sinusoid, suddenly it looks much more jagged and non-sinusoidal. And we also see that change reflected in the torque. At the point the step occurs, we really see some huge 20 Newton meter swings in the torque, including going into negative. And even when the system settles out kind of to a steady state with that 6-step excitation, we've still got really big torque swings there, and it looks much less sinusoidal and clean. So if we were to take an FFT and look at the PWM versus the 6-step, we would see a lot more harmonics and higher amplitude harmonics in this signal. So the torque swings in that 6-step excitation are going to cause all kinds of vibration issues in that system. Another example, a torque ripple from a permanent magnet motor. So here we've had several customers that take a set speed for their system and then they step it through a variety of torque values, and they're creating what they call a torque ripple map. They're just interested in seeing, how does my torque ripple value, my torque ripple percentage value, change as my speed is constant and my torque changes. So in the graph, we're looking at the red is the current, the blue is the torque. And in this particular case, we've picked out one of the worst case scenarios, just so you get a really clear picture. You can see you've got plus minus 4 Newton meters of torque ripple on an 80 Newton meter average torque, which is a pretty high percentage. And in this case, the user was interested in really understanding what that value was, and then being able to work on ways to mitigate that, to minimize it so that it didn't affect their application. And that is something that you can do with the HBK edrive power analyzer. A final example, looking at torque as it relates to control changes. So in the top graph, we're looking at an XY plot of ID versus IQ. What they did during this test was provide or apply a large D-axis current step onto the motor and then look at how the torque responded. So you can see the current step in the middle and then the torque versus time below. So you can see that torque react when the current step is applied. The goal, the black circles shown on each of the ID/IQ graphs, show the expected and acceptable operating range for that motor. So the goal was to keep the values inside that black circle. When the operator sees the data go outside the black circle, they know that machine isn't operating the way they want it to, and so they're going to make sure that they don't, whatever step caused that excursion from the black circle, they're going to say, we got to make sure our product doesn't operate in that way. So being able to record all of the currents and the voltages, calculate those ID/IQs, look at everything in a correlated way, really made it possible for them to analyze this data. Finally, I'm just going to go through a few of the technical details of the HBK solution for torque ripple measurements. The edrive power analyzer is based on our GenDAC mainframe. We have a variety of sizes of mainframes, but you can measure up to 51 power channels in a single mainframe. By a power channel, I mean one voltage, one current that then combine to give you a calculated power result. These systems can operate either in a continuous streaming mode or calculating just recording set points or snippets of data at a specific set point. And you've got support for up to 6 torque transducers in a single mainframe. So that's 6 torque and 6 speed measurements that can be supported. Our 3-channel power cord is kind of the workhorse of the power analyzer. You can see the 3 voltage channels on top. Those can take in plus minus 1500 volts DC directly. And we have probe options if you need to go above that 1500 volts DC. It also has 3 current channels. Those current channels can take in either voltage or current, so you can use a variety of current sensors in your measurements. The module supports up to 2 megasamples per second sample rate with an 18-bit digitizer, and has an accuracy, typical power accuracy of 0.015% of reading and 0.02% of range. The beautiful thing about this card is it has an onboard DSP where you're getting all those real-time power calculations processed, but you also have access to that DSP to create your own calculations and get that information in real time from the system. We've talked about the high accuracy HBM torque transducers. We also have a line of current transducers that provide stable and accurate current, both DC and AC current measurements. There's a variety of other options that can be added to the mainframe to also support CAN bus recording, EtherCAT, publishing, and various inputs for noise and vibration, say accelerometers, microphones, temperatures, and also a module that can support higher sample rates up to 250 megasamples a second. So I will turn it back over to Shannon for our Q&A.
Awesome. Thank you, Krista. Yep, at this time, go ahead and enter in your questions in the Q&A panel. All questions will be answered by Krista. Again, just another reminder, the presentation will be emailed to all attendees. The webinar will also be posted on the website as well. So once that is uploaded, you will receive the link to that. Well, let's double check. Give everyone a couple minutes to type out their questions. Let's see here. How can I find out if my torque sensor has an internal filter?
Important to know. If it's an HBM torque sensor, you can, of course, call us, and one of our application engineers would be happy to review your settings with you and look. We've got, for example, for the T12, a T12 assistant that allows you to connect to the torque transducer and really look into what the filter settings are and change them or adapt them to what you need to be. If it is not an HBK torque transducer, you should be able to find that information on the data sheet of the torque transducer and dig in and see what information that company provides for that sensor.
See here, what are the maximum number of power measurements I can make with the HBK power analyzer?
That will depend on which mainframe you decide to purchase, but if each power module supports up to 3 power measurements. And so our largest mainframe has 17 slots. And in that mainframe, if you fill it with modules, you'll be able to get 51 power measurements all in a single mainframe.
Okay, last one here. What are the limitations or bottlenecks to increasing the bandwidth of torque sensors?
It's an interesting question, but when you talk to our torque experts, it really comes down to the material used to make the torque cells. So you need a material that's rigid enough to hold up at the higher torques, but also responsive enough to give you the bandwidth that you're interested in. So HBK has been putting a lot of effort into materials research and investigation, and trying to, with the goal of being able to increase that bandwidth in our next generation torque transducer.
All right, Krista, I think that's it for questions. We'd like to thank everyone for joining us today. We hope you enjoyed today's presentation. Again, a recording and copy of this presentation will be emailed to all attendees. Please contact Krista if you have any other questions at all. Krista, do you have your contact information on the last slide just in case?
If I don't, we will send it out when we notify you that I don't know that I put it on there, which I should have, but we'll definitely share it as we share the information that the recording's available, because you are welcome to contact me.
Awesome. All right. Well, on behalf of myself and Krista, we thank you again for joining us, and we look forward to your attendance at our next webinar. Thank you, everyone.
Thanks, everyone.